3 in-person talks in the next session, or the special session, or virtual talks with a diverse set of speakers of different backgrounds. Our first speaker is Carla CHIASSERINI, who got her laurea degree, I think, in Florence, and her PhD in Torino. And then she moved for a few years to the University of California at San Diego, returned to Torino, where she's now a full professor. Yeah, she is an IEEE fellow and has a vast conference and editorial experience, in particular as a member of the executive committee of the wireless transactions, and then as the editor-in-chief of Computer Networks.
Thank you, Martin. Thanks a lot. Okay, so I hope you can see well. Perfect. So the title of my talk is Crowdsourcing Learning, Leveraging Connected Cars in Machine Learning Tasks. And indeed, I will try to convey, I say, some issues, relevant issues, when we apply machine learning for the decision processes that we have in autonomous and also automated cars. So let me start with an introduction and motivation. As we know, today's vehicles are generating lots of data. So we talk about 25 gigabytes for modern cars, or up to 3 terabytes per hour for autonomous cars. And that's a lot, clearly. So this is very valuable. And they suggest that indeed this data can be used for our vehicles to make decisions. And therefore, they suggest that machine learning could be indeed a great approach to apply. The data are generated by sensors, and they relate also to the kind of maneuvers that our vehicles will perform. So examples of machine learning based applications that are used, thanks so much, I forgot to do that, that we use in our cars are, for example, the trajectory estimation. We already mentioned that yesterday. And indeed, we are doing some work also on this respect. Trajectory prediction is extremely useful for safety applications, as you can indeed forecast the position of a car in the next 2-3 seconds quite accurately. We are also working with colleagues from the mechanical engineering department on adaptive cruise control. That means to control the speed, so acceleration, deceleration of vehicles, and in order to guarantee a certain vehicle stability, so safety, but also comfort for the passengers and an efficient use of the road's capacity. So, for example, we have these cat-in and cat-out scenarios. The cat-in is a very challenging one. When a vehicle would like to move from one lane to the other, and on the other lane, and there are 2 consecutive vehicles, and you have essentially fit into the 2 vehicles, and then all the 3 cars need to determine the speed, so acceleration, deceleration, that they should adopt in order to let this maneuver happen safely, but also without leaving too much room between consecutive cars. Otherwise, the efficiency of the road usage essentially decreases. And I must say that in these cases that we are dealing with, machine learning is indeed extremely effective. So this is also a trend that has appeared in standardization. So in 3GPP standards, they explicitly refer to the case of machine learning based applications, not just for vehicles, of course, but also for the so-called vulnerable road users. So pedestrians, cyclists, bikers, and so on. And as the Volkswagen CEO said, so it looks like indeed autonomous driving and also the reduction of emission due to mobility really needs machine learning, in particular, I mentioned AI and deep learning. So everything looks good, but a recent study from Ford actually highlighted that the power cost of the connected and automation subsystem in vehicles has got a significant cost in terms of power consumption. And you can see here that in particular, the power cost due to the different sensors, but also the computing that happens in a vehicle with such characteristics is extremely relevant. And unfortunately, also the carbon footprint, so the greenhouse gas emissions that are due to this kind of subsystem. So depending on the type of vehicle that we consider compared to a vehicle where we do not have connectivity or automation, well, we have an increase that ranges from 3% up to 20% of increase in emissions. So the takeaway message here is that vehicles have lots of data, and we see that machine learning based decision making is extremely effective. However, we need to make this machine learning support in vehicles sustainable. And therefore, we need new solutions. And since our vehicles are connected, well, then a natural way to go seems indeed to exploit cooperation. So is this an effective way to go for? Well, if we think about machine learning, recent emerging trends in machine learning, this is indeed can be a quite effective approach. So very couple of slides on machine learning. We know that machine learning tasks are becoming pervasive. In particular, one of the most popular types of models, machine learning models, is the DNN, so deep neural networks, where we have an input layer, several intermediate layers, and then the output layer. This is an example that refers to a classification task. So you have an image representing, for example, an animal, and you have to essentially detect which animal is that to classify essentially the object or the living being. And our networks, in order to perform classification, needs to be trained. So they need indeed to learn. So we have to determine the weights essentially associated with the edges that we can see connecting the different layers between neurons. And this training process is very complex and costly. So we need data, and we need also computing resources to perform that. And the more sophisticated the model is, clearly, the more layers we have to consider and train. So that may be indeed quite heavy. And just to add a couple of details, when we train the network, the most popular method to do that is the so-called stochastic gradient descent. That essentially means to perform a forward pass from the input to the output. Then you have the comparison essentially in supervised learning against the ground truth, and then you compute the gradients during the backward pass. These are propagated from the right to the left of our network. This is a single iteration. In order to achieve a very good accuracy in your decision process, then you need, in general, to perform several of these iterations. But recently, as we know, we have some distributed learning approaches that are becoming extremely popular, widely used, and one of them, probably the most famous one, is federated learning that has been introduced by Google. So in this case, the idea is that you have several nodes that will participate in the training of, for example, a DNN. So you can use the computational capabilities of different nodes, and they will share essentially the burden of the training. So we have a server that is typically in the network infrastructure. And then the other nodes can also be, of course, mobile nodes. So in our case, they can be vehicles. The server will provide the same model to all the vehicles, to all the learners that contribute to the training. Each vehicle will train the model locally using its own data, and then they will return the model to the server. The server at this point averages across all the weights provided by the learners, and again, delivers to the learner the updated model to start a new epoch, a new iteration. So this is really good, especially in terms of privacy, because in this case, every node, every learner can, let's say, keep its own data local, no need to share them with others. And as we said, we share also the computational burden. However, there are some drawbacks, very serious drawbacks. One of them is the network overhead. The network overhead due to the fact that you need to transfer the weights of the model back and forth. And the amount of data this corresponds to is very significant. So this is a big problem that we have, especially, of course, in this wireless scenario. And the other one is the fact that learners may have different characteristics. So they may have indeed different computational characteristics or also connectivity capabilities. And when there is a learner that is slower than the others, actually you slow down the whole training process. And in general, when you train DNN, for example, you have it as a target both the accuracy in, for example, the classification task, but also the learning time. So you like to complete this training by maximum, let's say, time value. So this is just an example of some results that we are actually deriving these days using real-world platforms for federated learning. We are using Flower, but we are also using the IBM Federated Learning platform. And it's a very simple experiment where we have on the left the case where there is the server and two learners called also clients. And in this case, they are both fast, while on the right, there is a learner that is slower than the other, and it has got 150 milliseconds delay. So the amount of data that they exchange globally is the integral essentially of these curves is the same, but even if it's not represented very clearly, but on the right, the delay of one of the clients actually leads to a 15% latency increase of the overall training time. So this problem is real. However, there are also some techniques that we can use in order to mitigate this issue. One of them is to look at the averaging step in the federated learning procedure. So when the server receives the parameters from the nodes, from the learners, and averages them. So indeed, we can try, let's say, and optimize this step. So select the averaging technique that accounts for how fast the different nodes are, as well as also the type of data, the statistics of the data they own. So this is essentially falls in what it is the learning how to learn. So learn how to optimize the training process. And just to show you a couple of results that we have derived in a simulation. So this is just simulation, considering nodes that own different types of data. So some, the gold ones, have lots of data and statistically rich. So they see essentially 10 classes. Then we have the silver that have a little bit fewer data, bronze and garbage, that's what we call them. And then the different weighting strategy at the server, uniform, or the case where you account for the number of samples that the learners own, the number of classes that essentially they see, and the entropy of the data set that they own. So In this case, we can see that essentially the uniform, that is the standard way to average the weights, does not perform very well, while instead the entropy provides better performance in terms of accuracy and also in a sense learning time. And indeed, if we look at the local training process at the different nodes, we can see that in terms of time, the gold ones that have lots of data and statistically, let's say, irrelevant, they are extremely slow, quite good because they can achieve a high accuracy, but they are definitely slow. While instead, if you select the silver nodes, then you achieve more or less the same accuracy, but much faster. So this suggests that the problem of having nodes with different characteristics and data statistics can be a little bit mitigated if, for example, you select the learners with some intelligence. But the other problem that we had and that we have not solved yet is the high overhead. And this, as we were saying, in a wireless environment like the vehicular one, is indeed a big issue. So what I'm going to discuss next is indeed a scheme that tries to address this specific aspect of data transfer during the distributed learning scheme. This again an initial work that started actually from the virtual edge work with Falco, Vincenzo, and our co-authors. So we are continuing this vehicular environment where indeed we have, for example, a server in the edge. Let's assume that, even if, as Falco said, it might be a bit futuristic, but let's assume that we have this possibility. And vehicles can communicate with the server through vehicle to infrastructure communication. But clearly, we have also the possibility to let vehicles to communicate between each other. So we can also have V2V, vehicle-to-vehicle communications. So given that, of course, federated learning could be applied more or less as is in this kind of scenario. But there are actually other schemes that could be leveraged as well. So one of them is gossip learning. Gossip learning is, again, a distributed learning scheme, but in this case, there is no coordinator. And each vehicle trains a given model with own data, and then it can transfer the model to another vehicle that emits, essentially, while moving around. And then when a vehicle receives trained models from the others, then it will average locally the weights and obtain an updated model. So this scheme has clearly some advantages. So there is no dependency on the central infrastructure. Therefore, we are more robust with respect to mobility of our vehicles. It's more scalable. But on the other hand, the performance depends indeed on the network topology, because if there are groups of nodes that at a certain point become, let's say, they get out of each other radio visibility, well, then they will train essentially the models differently. So they will not converge to the same model. And this may be indeed an issue. So what we thought was that we can actually consider a kind of combination of the two. So we said, let's try to put them together, get the most out of the two paradigms, and consider that we have a server in the edge that provides the model to some vehicles, but these vehicles will be just few, and they are called group initiators, because then each of them can actually start a sort of gossip learning, kind of, because actually they're going to perform a given number of hopes, and each hope a vehicle can essentially improve the model, further train the model with its own data. And the last one of the group will return the model to the server. And then the server performs also an average across these models, and again, repeats the process for a new round. So if we do that, we saw that indeed the performance in our training process may improve significantly. Again, these are initial results. On the left, you have the accuracy that you can achieve as a function of the number of transmissions, because remember that now our goal is to reduce the overhead of the distributed learning scheme. In this case, we used a very popular data set of images, not particularly suitable for vehicular applications, but it is what is used, let's say, often in the literature. And we compared our scheme considering 10 vehicles that overall participate in the learning process. And in the case where you have groups of 2 or groups of 5, against the case where you use federated learning and you involve, again, in overall the same number of nodes. And you can see here that indeed we can improve the accuracy with much fewer transmissions compared to federated learning. And then on the right, you have the results that we have derived considering instead data sets and application and machine learning task that fits, let's say, the vehicular applications better. In this case, the learning task is actually the trajectory prediction, and the data set refers to trajectories of vehicles on a US highway. And the results that we can see there are related to the accuracy in predicting the position of the vehicles, and on the number of transmissions that occur between the learners, our vehicles, and the edge node, the coordinator, as well as in terms of overall number of transmissions. So we can see that indeed we can achieve very significant gains. Now, as I was saying, and this is kind of preliminary work because there are still many open issues to address. First of all, as I mentioned, we considered IID data owned by the vehicles. We still need to complete our performance evaluation considering instead non-IID data the vehicles. We know that in general, federated learning doesn't perform very well when we have non-IID data. So that's usually an issue for federated learning. What we are seeing when we apply our scheme instead is that we are obtaining very good results. Of course, not as good as when you have IID data, but much, much better than the performance of federated learning in the same conditions. So this is indeed very promising. We still need to assess also in this case the impact of the delay in local learning. So when indeed one of the vehicles, for example, is slower than the others, to try different averaging techniques. And then, of course, we will need to optimize the parameters, the configuration of our Eagle scheme. That is, for example, the number of groups to use, the number of vehicles per group to use, and how to select the vehicles that will be part of the group. So this is also a challenge from, let's say, the modeling part of the work. And we need to consider and account for the impact of the vehicle's mobility and the wireless channel. Why? Because there might be some vehicles that are part of the group initially, But then, due to mobility or to harsh channel propagation conditions, they may be unable to return their locally trained model to the server. And in this case, then the server, of course, has to go on with fewer number of models. So this is what is called asynchronous federated learning in the literature. It performs worse than the synchronous case. So we need to see what is this impact on the performance of our schema, Eagle, and what is the minimum acceptable number of models that we need at the server, depending, of course, on the data that we are dealing with, the machine learning tasks that we are dealing with, and perhaps to design schemes to introduce some redundancy in order to make the overall scheme more robust. So this is just to say that there is lots of work to do still, but if I have few more minutes, I would like also to mention that federated learning, gossip learning are not the only distributed learning paradigms that we have available today. There are more, and indeed pushing forward towards distributed learning, an interesting paradigm that is being proposed is split learning. So split learning is, let's say, more advanced because in this case, our learners can actually train part of the DNN. So while in federated learning, the server was delivering to the learners exactly the same model, the entire model, and each of them was contributing to the training of that model, of the whole model. In this case, instead, we essentially split the layers of, for example, of a DNN and assign to each learner the task of training a part, some indeed, of these layers. So in this case, for example, if we have the simple scenario where there is a node in the edge of the network and then a client, a learner that is a vehicle, well, then the vehicle can train the initial layers of the network, for example, till the so-called cut layer, and then send the output of the cut layer to the edge. The edge will complete the forward pass. Then we start the backward pass that will be completed then by the vehicle. And then, of course, they will repeat the process. So in this case, let's say, depending on the capabilities of the nodes of the learners, vehicles, they can be also nodes of the smart city, clearly. You can design the scheme so that everybody trains what it has the capabilities for. And this is indeed what we try to do with a scheme that we call the DNN trim. So we consider DNN and the fact that we have several layers. These layers can be also, let's say, instances of the same layer can be replicated. And its training can be assigned to different network nodes. And then we can allocate at each node the right amount of resources in order to complete that training. And the objective would be, again, to minimize the energy consumption, the overall energy consumption. So the overall objective is still to make ML, let's say, sustainable. And we have the constraints, again, about accuracy and learning time that we have to account for. So what we did was, indeed, first of all, to select, given a DNN architecture, select the graph, let's say, that representing the layers of the DNN that will lead to a feasible solution in terms of accuracy and learning time, but that hopefully are also able to provide low energy consumption. And then given the DNN structure, we mapped essentially the layers onto the nodes, accounting for the capabilities of the nodes themselves and the data that they own. And I don't want to go into the details, but essentially this mapping step was solved by using a delay-aware Steiner tree. And at least now we have, let's say, the mapping between layers and learners that are involved into the process. But this is still a temporary, let's say, solution, because then we can try and optimize, as I was mentioning, the amount of resources that each node actually devotes to the learning task. And of course, the objective is to reduce as much as possible the amount of resources that are consumed. So this last part of the problem is actually convex. So we like that, and it can be solved optimally. And then we can actually try to aim at the minimum energy consumption overall by repeating the whole procedure, the three steps. And what we found is actually that this overall scheme has a polynomial complexity, computational complexity, and also we computed the competitive ratio of the scheme that we came up with. So let's say this is again an initial work. We have a few results that we have derived already. These are in terms of total energy consumption as a function of the learning time. And so we compared against the split learning, so SL split learning, as well as against the optimum. So what we can see is that we can gain a lot with respect to split learning, especially, let's say, when we have time. So if we have time, we can, let's say, trade off time with resource consumption, energy consumption. And in that case, our scheme can really contribute to make machine learning more sustainable. Let's say, overall message that I would like to deliver, wrapping up what we presented, is therefore that in many applications, and working also with real world applications, we have the evidence that machine learning is an excellent approach in let's say, for autonomous and connected vehicles. So I don't think that we can do without that, but at the same time, it has a significant cost. So it is certainly worth it because many safety applications are based on machine learning and they work well. And when, of course, humans' life at stake, this means that these approaches are definitely worth it. But on the other hand, there is this awareness that is emerging that we need to make machine learning sustainable, and in particular for our vehicles, it must be so. So as we stand, one technique is to exploit distributed learning schemes that exist. So our goal was not to propose, let's say, a totally new distributed learning scheme, but to leverage what it exists and to adapt essentially these schemes in order to make them suitable for our vehicular networks. So this is essentially what is often referred to as networks for machine learning, as opposite to machine learning for networks, right? So we started with some more widely used paradigms like federated learning, and tried to solve the problem of data overhead that is there, that is huge. And then what we are doing is also trying to exploit the most recent paradigms in terms of distributed learning, like split learning, and really try to match what we have in the network and configure the network in order to optimally support these learning paradigms. So as I said, there is still lots to do, and in particular, what we would like also to do as next step, besides optimizing the schemes and further investigating these schemes that we are coming up with, would be to consider the overall system that we have in an urban environment. So including vehicles, smart city nodes, and also the vulnerable road users into the picture in order to involve essentially all of them. So thank you very much for your attention. And if you have any questions, I will be happy to answer. Thank you.
Okay, thank you. It was very, very interesting. I have one question about whether you are also looking at what happens if one of the nodes in the cooperation is not cooperating in a good way, either because it has bad data or whatever, and how is the impact on the accuracy or on like the application?
Yeah, thanks a lot. Yeah, this is indeed a very interesting aspect, and there are many people who are actually looking at the security aspects of federated learning and also privacy, because as I mentioned, let's say a big advantage of federated learning is that we keep the data, the original data, let's say local, they are not shared. So federated learning is known as a privacy aware distributed learning approach. But actually, it seems that even sharing the weights of the model may actually lead to privacy leakage. So that's one aspect that I mean, we are not looking at that, but there are researchers that are focusing on that. But absolutely, with respect to the robustness of the scheme to attacks, when you know, some nodes may actually inject false, let's say, weights. So there are some works that have been done in that respect, and essentially what they do when there is the coordinator, like in federated learning, the coordinator should make a check on the weights and see which weights deviate, let's say, too much, and remove them from the averaging operation. So some, let's say,
that could be valuable data that is not seen elsewhere.
So yeah, exactly. So there is a trade-off, right? So what the server in the edge does is to work with weights. So not the original data, but the weights of the model. And as you said, there is a trade-off, right? Because if you are excluding some data because they are too much off with respect to the others, well then kind of you protect your process from attacks that tend to deviate indeed from the reasonable, let's say, process. But on the other hand, they in the case where the nodes have data that are non-IID, so indeed they may actually compute weights that are some of them weights that are very different from what the others computed, and they could be valuable and rich in terms of information, but you are excluding them, right? So as far as I know, there is no final, let's say, definite solution to address this issue. But yeah, thanks for the question, because this is indeed a very important aspect. We have not looked at that yet, but certainly it would be worth it to pursue. Thanks. Yeah.
Bonsoir. Yeah, thank you for the nice lecture. I was wondering, so in this federated learning setting, when you alluded to the case of a graph, which would be not connected, and the possibility of convergence to different limits, right? But so assume this graph would have motions, like other conditions for convergence of the federated learning in case of motion, and because you have this combination of averaging and update by training, local training, right?
Exactly, yeah.
And so does one know in this case sufficient condition for convergence of the whole thing?
So I'm aware of, because we are reusing some results and trying to extend some mathematical results that indeed have modeled the convergence of federated learning. And also, let's say, as the number of nodes participating in the training process varies from, let's say, epoch to epoch. So that's something that we can account for. And that's, let's say, a relatively simple, manageable, tractable mathematical model for convergence. However, in general, I think that this is a very interesting field, because I mentioned just some of the techniques that are there, but another very interesting technique that is there, for example, is knowledge distillation that has been there for many years, or I'm sorry, or transfer learning. So in these cases, for example, we were looking for some of these mathematical derivations about the convergence in the case of transfer learning, but there are no models, at least that we found so useful so far. I think because especially, for example, for transfer learning, it depends on the data, on the features that essentially you have, and the model that you get from others was trained with. So it is probably very much related to the type of data that you deal with, right? But I think that in general, for future studies, it would be extremely interesting to see if there is the possibility to characterize the data statistically, and then see, given the statistics of the data that you used to previously train the model, and now the statistics that you have to train the new model, if you can say something about speed of convergence, right? In given the statistics of the data as an input. So I'm not aware of any works on analytical works on that, but yeah.
There might be connections with bounded confidence dynamics, which that is the local averaging, and there are versions with an additive noise, for instance, right?
Yeah,
And,
you're right.
So there are mathematical when you have a graph and interactions, local interactions.
Yeah, that's
so,
indeed very interesting.
Yeah, so it's a beautiful question.
No, indeed. I mean, it's a new field. At least this mathematical characterization of the process that deviates from the standard, let's say, federated learning, and looks at other types of learning that are emerging these days, or are more, let's say, they are widely used these days. I think it's really promising, and there is lots to do. It would be very interesting, actually, to, yeah, I will get in touch with you as well.
Or thank you very much. Or the main question has already been asked, but so if we try to apply this federated learning to some dynamic structures, like what Sylvester was talking about, like connected vehicles and whatever, do you know or any good results explaining how, for instance, the convergence times or the quality of the metrics depends on the stochastic characteristics of the process, the nodes coming and go? If you have like 100 vehicles on average, but some of those start disappearing randomly, like what could be the best strategy there, and how bad it is for the learning itself? Yeah.
So we are doing some work about this. So we'll be happy to share some work that we are doing that is indeed trying to account in an abstract manner, of course, the varying number of nodes that we have in the process, as time goes by, and we move from one iteration essentially to the next one, right? So it depends, of course, also on the type of data that they own. In terms of amount of data, to account also for the amount of data that they provide, that's feasible. To account for the specific statistics of the data that they own is a bit more difficult from the mathematical point of view of the modeling. But yeah, I will be very happy to share some work with them. Thank you. Thanks.
Any other questions? Yeah, I was curious about the time scale we tackle in these scenarios, vehicular scenarios, etc. Because, for instance, I could say that for training, we just need a deadline of 3 months. Because, I mean, we train, we don't get, so we have to be fast in inference. I want to infer the trajectory. But if I spend even 3 years training a good model and improving it very slowly, maybe it could be enough, and so I could just target energy efficiency. So what is your opinion?
Yeah, I mean, I think it depends on the, let's say we are doing some work on trajectory prediction with also real world data that we obtain through drones, etc. Anyway, so the fact is that the context, the environment where you are, and the conditions in which you are actually are important, have an impact. So I wouldn't say probably 3 months, because like the layout of the intersection for any reason may change and so on, and also let's say the other vehicles that are there and how they move, of course, have an impact, right? Because it's a system where everybody interacts with everybody else in the area. So what we noticed at an intersection is that if we vary the mobility, we try that actually with Sumo to vary the mobility of the nodes that are around. And so depending also on the time of the day, the density of the vehicles, the presence of vulnerable road users and so on, actually the trajectory prediction model can work much better if you account for all this information. And that means that you have to update essentially the model, let's say quite often, depending on the conditions that are there. So those are indeed the space and time varying. But it's true that it really depends on the application that you are targeting. So for some applications, I totally agree that you have a time span that allows you, to also to optimize things. And even if the overall consumption may be high, but at least, as we were saying, if you have time, you can reduce the consumption as well. Yeah.